And the thing to remember about arguments is that you're going to have a sequence of hypotheses which you are claiming are true, and then you're using your hypotheses to justify your conclusion. And there's this technical word in arguments that we need to remember: valid. So in deductive reasoning, when we're doing logical arguments, the word valid has a very specific meaning that's a little bit different from the way that it's used in everyday speech. And what it means is that the conclusion must be guaranteed to be true by the hypotheses. So in everyday speech, valid might mean something a little bit different, or a little bit looser. Here we mean if these hypotheses are true, then the conclusion must also be true. So it's very specific. And then we also talked about what symbolic arguments look like, because often we want to think about structures of arguments instead of concrete arguments in English. Because when we think about structures, maybe we can answer questions about lots of arguments all at once instead of just a single one. And the idea, the structure is fairly simple. You're just going to stack your hypotheses on top of each other and then separate your conclusion from the hypotheses with this horizontal line. And then you write your conclusion. And the symbol, the 3 dots arranged in a triangle, stands in for the English word therefore. And you'll see that symbol pop up in other places in mathematics sometimes. That's what it always means. It means you're about to draw a conclusion. Let's see. And then the next important thing I want to be sure to review are these. These are the what get called the rules of inference. And you should remember that these are brief, simple arguments that are always valid. So if you use one of these simple arguments, or if you use some combination of these simple arguments, then your more complex argument is always going to be valid. And these 7 are the ones that show up probably the most often. So they get special names. And I don't want you to focus so much on the names and making sure you memorize what they're all called. Mostly you should just be familiar with how they work. Let's see, and this is where we ended the class. Last time we looked at an example of a fairly simple sort of reasoning or an argument that you might make in everyday life. And well, you probably remember what it was. It's a silly example about picking a restaurant on your birthday. And it turns out that the simple argument was this thing called a hypothetical syllogism. So even though it sounds complicated and fancy, you know, you're putting 2 words together. You probably haven't really ever seen this word before, together with this other not very common word. But it's actually a fairly simple common argument. And that's why it's a rule of inference. Are there any questions before we do the other examples here? So let's look at another argument, this one. It says if 2 is equal to 3, then I ate my hat. I ate my hat, therefore 2 equals 3. And what we want to do is determine if this argument is valid. So I want to remind you again that valid in arguments means something very different from what valid means in everyday English. If someone made an argument to you that included this phrase or this proposition, I ate my hat, you would immediately think that their argument is ridiculous, and you might even think your argument isn't valid or something like that. But in logic, it's possible to have a valid argument where one of your hypotheses, this one, could be totally ridiculous. Valid just means if it's true, then your conclusion is true, which is a bit different. So let's break this down and translate it into a symbolic argument. And there's two pieces here. If 2 equals 3, this mathematical proposition should be one of our simple propositions. We'll label it P. And then the second part of this conditional statement, I ate my hat, is another proposition, which we're going to call Q. So the second proposition is Q by itself. So you're claiming that Q is true. And then our conclusion is P again, 2 equals 3. And let me write some of what I said down. So we're labeling P for 2 equals 3. And Q is going to represent I ate my hat. So probably by now you've noticed that when we're talking about logical propositions, instead of writing P equals a statement or Q equals something, instead we usually use a colon in place of the equal sign. But you've probably picked that up just by watching and reading. So now I want to use these symbols to rewrite this symbolically. The first hypothesis is if P, then Q. So we'll use the symbol for a conditional proposition, the arrow. The next hypothesis is the proposition Q. And then the conclusion is the proposition P. So is this valid? Well, if you're not sure, one way to quickly determine if it's valid is to go back to your list of the rules of inference and see if the argument shows up there, if the symbolic argument shows up here. So does this argument, is it one of the rules of inference? Anyone? Is this argument one of the rules of inference? Yes with a question mark. You're not sure. So it's actually not a rule of inference. It looks very similar to this one, modus ponens, that says if P then Q, P, therefore Q. But on this particular argument, P and Q have been switched. So this actually is not a rule of inference. And actually, this one is not valid. So it's possible that it could be valid even if it's not one of the rules, but this one is not. Excuse me while I silence that. There we go. Okay, so as I was saying, this one is not valid, and I'll explain the reason. If P is false and Q is true, so I guess let's back up just a second here. So if an argument is not valid, we're trying to find an example where the two hypotheses are both true, but the conclusion is false. So if P is false and Q is true, then the first part of the argument, the conditional, is vacuously true because the hypothesis is false. So let me just put a T here. Maybe you'll make an extra column. And I'm also saying Q is true. So this hypothesis is also true. But P is false. The conclusion. So I've come up with an example where this is false, where the conclusion is false, but the two hypotheses are true. Okay, so if you run across a problem like this and you're not sure what truth values to plug in for P and Q, then the method that's always going to work is to go back to this example from last time where we were looking at this symbolic argument. And what we did was we made a truth table with columns that had the two hypotheses and then another column for the conclusion. And if you fill out this truth table and look for the rows where the hypotheses are true, then you need to find a true conclusion in order for the argument to be valid. So if you're not sure what to plug in here, what truth values for P and Q to use, then you can make the whole truth table to find the answer. Okay, so is this, well, I already answered this. It's not valid. I don't have to ask you again. Are there any questions? Okay, so it doesn't sound like there are any questions. And I want you to remember this example, so this logical symbolic argument, because it's actually fairly important because it's one of the common fallacies. So a fallacy is an argument that's not valid. And this is sometimes called the fallacy of affirming the conclusion. And the reason why it gets this name is that Q is your second hypothesis here. You're affirming that the conclusion is true. So this is a conditional statement with a conclusion, and this affirms the conclusion. Okay, and we have one more example here. Moving on to an argument that's a little bit more complicated because, well, it has more hypotheses. We have 3 instead of just 2. So what we want to do here first is break this down into a symbolic argument and then try to determine whether the argument is valid. And there's a few pieces here. Well, maybe we should just read it first. It says the bug is either in module 17 or in module 81. So in this example, you can imagine you've written like a big computer program or a piece of software with multiple pieces, multiple modules. You know it has a bug, and it's either in module 17 or module 81. The bug is a numerical error. Maybe the result of your program is a number and it's not giving you the right number. And we also know that module 81, this one, has no numerical error. So maybe we've already checked it. The conclusion is that therefore the bug is in module 17. So let's break it down. The first sentence has 2 pieces. The bug is in module 17, that's one piece. And the other piece of the or is the bug is in module 81. So let's give those 2 the names P and Q. And then the next proposition is the bug is a numerical error. That's its own separate piece. And then the other two propositions, the last hypothesis and then the conclusion, these both have to do with the ones that we've already written down. So we don't need to add any more letters for those. So now we get to rewriting this using our symbols P, Q, and R. The first one says that P or Q is true. Right, the bug is in module 17 or in module 81. So it symbolically, we would use the or symbol, the V, for P or Q. And then the second one here asserts that the bug is numerical error. That's R. And then the last one says module 81 has no numerical error. This one is a little bit more hard, a little bit more complicated to translate into these symbols. But what we're saying here is that if the bug is numerical, so if R, then the bug is definitely not in module 81. So that's R, or if R, then not Q in symbols. And then the conclusion is P. Okay, so it looks like we're at 12:50. So if you need to leave, you can go ahead and go. This will only take me a minute or two longer if you'd like to stick around. So the reason why this won't take us very long is that we can break this into rules of inference. For example, this one, we can take this hypothesis, if R, then not Q, and this hypothesis R. This is similar to modus tollens, or sorry, the other one, modus potens. This is the first rule of inference. And you can remember that the conclusion was this, or it corresponds to what this is, not Q. And this is a valid argument. We don't have to think about it anymore because we know it's valid. It always works. So I have a new true statement that I can use. So I can look at P or Q and this new hypothesis, not Q, which I also know to be true. And then I can conclude, if we go back to our rules of inference again, number 7, the or statement, you say that one of them is false, and then you conclude that the other one must be true. That works here. We have P or Q, but we know this one is false. So we can conclude that P must be true. That's the disjunctive syllogism. And that's what we wanted, P. We wanted to guarantee that P was true. So we broke down this 3 hypothesis argument into 2 rules of inference to show that it actually is valid. Okay.